Okay, hello everybody and welcome to my next video on optimization with cylinders. A little while back I did a different optimization video where we used technology and we were helping out the company H2O Go. Well, H2O Go is back again and this time they want to create another cylinder tin. However, they don't want it to hold just a litre this time. No, they're expanding it for industrial purposes to help out other businesses with a 100-litre tin available from H2O Go. So what do we have to do? Well, we have to design the tin. And again, H2O Go doesn't like spending a lot of money because they want to get their profit margins as high as they possibly can to impress the investors, of course. So what we're going to need to do today is we're going to need to actually make this 100-litre tin can have the least surface area, or the lowest amount of surface area possible, so that they're able to produce it in mass. Okay, so 100-litre tin can, and instead of using technology this time around, we're going to use calculus. So we're going to differentiate it, and we're going to be able to get something from that as well. Okay, so optimization. Well, first off, there's two sort of variables we really need to know, or get the hang of by the end of this. And they are related, of course, because, well, we have a volume, so therefore the values will be related to the volume that we have in terms of that figure. So a little conversion first off, because we need to work with a length measurement rather than a volume measurement. We don't want to work with a litre, we want to work with a metre, even though they rhyme. Okay, so how do we convert 100 litres into metres? Well, 100 litres is going to be equal to 0.1 metres cubed. So that's pretty good, and from that we were able to get our head around what we're actually going to be doing in this process, because again, we're going to need to work with metres rather than litres. Okay, so now that we've got that established, we need to go on to the next step, and that is to actually calculate how we're going to use the volume. So, the volume equals, and this is for a cylinder, the general formula, the volume of a cylinder is pi r squared h. Okay, so it's a circle, you know, the area of a circle is pi r squared. Again, we're going to want to find the radius and the height, and we get pi r squared to get the circle, and then the height. It's just like having a circle elongated out by the height, really. That's all the surface area is. The volume is, sorry. The surface area is a little bit different. But now we know what our volume is going to be, because we know that 100 litres is 0.1 metres cubed. So we simply substitute it in. So 0.1 equals pi r squared h. And from that, we're able to derive the value of h by just using simple algebraic rearrangement. So what we do is we bring this, because it's in the numerator on the right-hand side, it's in the denominator on the left-hand side. So 0.1 over pi r squared equals h. Excellent, and we've worked out that h value, and again, that's going to be critical for us finding the lowest amount of surface area, because we've established a relationship between r and h, and we're going to solve for r. That's going to be our input value. What happens when we change the radius in terms of the output? And again, we want that volume of 100 litres. Cool, so we know what our h value is, and we can move on to the next step now, and that is to use a total surface area formula to be able to work out, you know, when the derivative of that equals 0, so we get the value where the total surface area is a minimum. Okay, so from this, total surface area of a cylinder is going to be equal to 2 pi r plus h. Again, it comes in handy to know all these geometry formulae. So what we can do here is we can get that, and that equals, we just expand using the distributive law, so we have this multiplied by r, and then this multiplied by h. Simple stuff, so we get 2 pi r squared plus 2 pi r h. Awesome. However, we know what h is relative to r. And look here, we have two inputs. We have two unknown pronumerals. We have r and h. But because we know this relative to r, we can only have one input now. You know how great that is? It makes things a hell of a lot easier. So from that, what we do is we simply substitute in h. It's that straightforward, really. So 2 pi r squared plus 2 pi r lots of 0.1 over pi r squared. Awesome, and now what we do is we expand this using distributive law, because again we can simplify it down, and making things simple, especially when we're looking at areas like this, is going to be something that's really beneficial for differentiation purposes. So we have 2 pi r squared plus, and then what we do is we have 2 pi r times the numerator, so we have 2 pi r lots of 0.1 over pi r squared. Awesome. However, we can cancel down, and cancelling, again, like expanding, makes things a lot simpler. So, let's see, there's a pi in the numerator and a pi in the denominator, and they're both multiplied by other values. Okay, by pi. We can cancel them out. Really good. Now what we can do is we can cancel out the r in the numerator, and because we cancel out one of them, we just take one of them out in the denominator, so we're left with 2 lots of 0.1 over r. Hopefully you can see how I did that. It's just basic cancelling. Nothing you shouldn't be too familiar with. You should probably understand what I did, but what we can do now is we can simplify it. So we have 2 pi r squared plus 0.2, because that's 0.1 times 2, over r. Okay, and then we have it, the total surface area formula. So the total surface area formula we can now differentiate. So this is TSA, and we can get TSA prime, the derivative of total surface area, and from that we will be able to set that to 0, and based on the curve properties video you'll know, oh, it's a stationary point, and so it's probably going to be a minima or maxima. And we'll even construct a sign diagram to be able to check whether it's a minima, because how terrible would it be if we told H2O go the maximum dimensions for our can? Because, again, that wouldn't go down too well. Okay, so now, in order to get this total surface area prime, we use the rules of differentiation that we've become so accustomed to. So first off, we have the first rule, product rule. We have 2 pi and r squared. We have two terms there multiplied by each other, and we're just going to differentiate them. Okay, so first off we differentiate the first term, 2 pi, and that's going to be a constant. Pi is a constant, 2 is a constant. When we differentiate 2 pi, it's like differentiating 6.28, because that's roughly what 2 pi is. So that is going to equate to 0. So it will be 0 lots of r squared there, as the first part of the product rule derivative. Because remember, we differentiate the first term, leave the second term as is. So that's going to be 0, not even going to bother putting it in there. Next, we differentiate the second time, and it's plus this value of the derivative of the second value. So in this case it'd be 2r, because we're treating r as an x value. It's not a constant, it's a pronumeral input value. And then, again, it's just the derivative of that, which is going to be 2r. Anything raised to the power of 2 is just going to be 2 lots of that anything. And then we multiply it by the first term as is. So it's 2 pi, 2r. Or 2r, 2 pi, depending on which way you read it around. Okay, and then we differentiate the second part of the equation. Okay, so what's happening here? Well, we're going to use quotient rule, because there's evidently a numerator and a denominator, and it's really helpful to use quotient rule instead of making our chain rule, because it'll probably be a bit nicer in this context, especially because we have a constant involved. So what does quotient rule say we do? Well, we differentiate the numerator first. What's the derivative of 0.2? 0. It's constant again. So we have 0 lots of the denominator, 0 lots of r. 0. Okay, cool. Then it's subtract the derivative of the second term. So it's subtract and the derivative of r. And the derivative of r is just going to be 1. So it's subtract 1 lot of the numerator as is. So subtract 0.2. And that is all over the denominator squared, r squared. And there we go. We have found TSA prime. Awesome. Now what we need to do is we need to solve for when that value is 0. So we're going to work out our radius. Okay, and I'll probably need to get a calculator out, so let me just go to my desk and, cover the light source for a moment and actually get this out. So, we can use our calculator to solve for the minimum, but I'm not going to do that. I'm just going to use that because there's pi involved. And I can't really work too well with many decimal places in my head. Not at 9:30 at night, anyway. So 0 equals 2r 2 pi. Take 0.2 over r squared. Therefore, and now we just use algebra. So, let's actually simplify it. 2r 2 pi is going to make 4 pi r. You should be able to see that. 2 times 2 is 4, and then there's a pi, and there's an r there. Makes sense. Okay, so now what we do is we move that, and it's negative 4 pi r. Again, I'm just taking it to the other side, so I inverse the operation. Negative 4 pi r take equals negative 0.2 over r squared, and therefore what we end up getting is we end up getting positive 4 pi r equals 0 over 2 lots of r squared. So you probably ask, well, how did you get that? And my answer is, well, we have a negative there, we have a negative there, and so we can both make them positive. It's like timesing by -1 on both sides. What you do to the left-hand side, you do to the right-hand side. So I can make them both positive. Okay, and now what we do is we bring the denominator of the right-hand side up to the numerator on the left-hand side, so we get 4 pi r, and let's use index laws here. So we have r squared times r, so that's r to the power of 1 times r to the power of 2, so we add the exponents and we get r to the power of 3 equals 0.2. Then, what we do is we move the 4 to the other side. So we get 4, we move the 4, so that's pi r cubed equals 0.2 over 4. And then we go to our little friend, the calculator here, or you could work that in your head. Again, it should be something like 0.05, I reckon, but I'll just check. 0.005 maybe? Divided by 4. Yeah, 0.05. So because it's 0.05, it makes things easier. And then what we do is we have 0.05 divided by pi. So I'm probably going to come up here, save some room. So we have r to the power of 3 equals 0.05 over pi. Therefore, r to the power of 3 equals, and 0, I'm going to have to round